Okay, today we're going to cover two sections from the book, but one of them we've already covered, so it's really not anything new, I guess, per se, because, we already talked about it. So let's just get to it. We're going to solve each of these. So I'm going to add 31 to both sides, and I'm hoping the pen works. It does. Okay. So what's that give me? 10, 80, divide both sides by 4. I'm going to get to here. Basically, it's just saying what can I square and get 20. There's two things, either positive or negative square root of 20. Or 20 is 4 times 5. So square root of 4 is 2. 1 squared of 5. Okay. This one, the same thing. We'll subtract 14 from both sides, which will leave me 6. I'm going to multiply both sides by 3. Divide both sides by 2. This one's either 3 or negative 3. This, you got x plus 3 could either be positive or negative square root of 5. And I have those answers. And remember, that's two different answers. Negative 3 plus the square root of 5 and negative 3 minus the square root of 5. All right. So that part, again, already covered it last week when we were just reviewing, and because it gave us some ways to work with square roots that were a little bit more than just find the square root of this. Oh, sorry, I got the office this morning. Okay, we talked about this last week too, because we solved by factoring, where if two or 3 or 4 or 5 things get multiplied to be 0, one of those factors has to be a 0. Totally useful. So if you've got this equation and you have to solve it, if I were to get everything on one side and set it equal to 0, it's hard to tell what x is in that form, but if I put it in factored form, this is just a trinomial with a lead coefficient of 1. What multiplies to be negative 45, adds to be negative 4. That's what a negative 9 and a positive 5. So what x value makes x minus 9, 0? 9. What x value makes x plus 5, 0? Negative 5. And we could check it. Like, here's what you'd be looking for. 81 minus 36. Yep, that's true. And we could check negative 5 the same way. But, we're okay. This one, again, if I get it all set equal to 0, and then it's a trinomial with a lead coefficient. It's not 1. And there's no way it's a perfect square because 3 is not a perfect square. Let's see how I can get it. If I do a 3x and an x, it'll give me the 3x squared. To get that 2, I need a 1 and a 2 or a 2 and a 1. I need to make a 5. Let's try the 2 and the 1. Because then here's 6x. There's 1x. I can make a 5 out of those for sure. And let's see if I can make the signs work. Because just because, goodness, just because you can make a 5 of some type doesn't mean this is the form it should be in. We've got to make the signs work. So the back has to multiply to be negative 2. So I need them to be different signs. And they need to add up to negative 5. So if it were a negative 6 and a positive 1, okay. So 3x and 2. There's this, oops, moved on me. There's the 6x being negative. There's the 1x being positive. And I think I look pretty good. 3x squared minus 5x minus 2. Yep. So what x value makes a 3x plus 1 equals 0? That's a negative 1/3. What x value makes an x minus 2, 0? That's a 2. That doesn't look great. Let me fix that. And just in case you kind of lost, I was just doing this part in my head. Okay. All right. Now this part's new. The zeros of a function are the x values that make the function. Why is it? Hang on, let me write that again. That looked weird. Okay, so the zeros of a function are the, I guess, because it doesn't have to be an x. I guess I should avoid that. Like these are all x's as the input value, but it's the inputs, I guess, that create an output of 0. That's why we call these the zeros of the function. So if I wanted this function to equal 0, then what I'm asking myself is what x values do I actually plug into it to make that happen? So, all right, I need the 2x squared on the front. Got to multiply to get 12 on the back. It's got to be the same sign because I'm multiplying to get positive 12. They're going to add it to be negative 11x. So I know they have to be negative. So I could do, let's see. Ooh, let's try a 6 and a 2 because there's 12 and 2. Nope, that's not going to do it. Let's see. What about a 4 and a 3? Because there's 8 and 3, that's 11. There we go. So the x values would be 3/2 and positive 4. So my zeros are 3/2 and 4. And what that means is, like, I'm going to pick the easier one to plug in. If I plugged in the 4, let's see, 16 times 2, that's 32 minus 44 plus 12. Yep. So like that's the x value that gives me out a function value of 0. Okay. All right, this one, same thing. I want the zeros of this function. And, ooh, it's a trinomial. The front and back are both perfect squares. If it's going to work, it's going to be a 2x and 7 because I square a 2x to get 4x squared. I square a 7. 14x and 14x do make 28x. There we go. So what makes a 2x plus 7 all squared equals 0? Well, the only way that's going to work is if it's a 0 getting squared. So what makes a 2x plus 7 equals 0? So that'll be a negative 7/2. So the 0 is negative 7/2. Okay. All right. Now this one, if you solve by graphing, it's pretty much the same thing as solving by factoring, because if I were to take this and factor it, what multiplies to be negative 6 adds up to be negative 1. That's an x minus 3 and x plus 2 when I get it factored. So now, like right there, this was the standard form of that parabola. Now this is the intercept form. Remember, the purpose of intercept form was to give you the x-intercepts of a parabola. And it's a parabola that opens up. Like, I could put everything more specifically, but if I'm just saying solve it by graphing, it's just the fact that, hey, I factored it. I can see when the y value is 0. So I know the x's that make that happen are at 3 and negative 2 because those are the x-intercepts. This one I would definitely bring everything to the right, because then you've got your lead coefficients positive. I would factor the 2 out. And then, ooh, that's a perfect square trinomial. It's an x plus 1 all squared. So what makes this 0? The only thing that does is a negative 1. Because if you were to graph it, it's just going to end up, that parabola is going to open up. It's just going to touch the x-axis, that one spot. So really, I didn't have to graph, but they're just trying to get, the book is just trying to get across that, hey, had there been a graph sitting there, that I could have just looked at it and found the x-intercepts, and those would have been the answers. Okay, so if a real number is a 0 of this function, then k is an x-intercept of that function, so they're saying k, and k is a root So pretty much they're just trying to get across the fact that a 0, an x-intercept, a root, we're all talking about the same stuff. It just depends on how the question is asked. So like if you've got x squared minus 5x, let's say plus 6, and you're looking for two numbers that multiply by 6, add to be -5. That'd be what? A -2 to -3? Okay, so if you started out with this, x equaling 2 and 3, those are considered the roots. If you started out with a function, then you'd say the zeros of that function are 2 and 3. Because if I'd plugged a 2 or a 3 into them, that would be the numbers that actually make this thing equal 0. 4, I'm just double checking. 4 minus 10. Yep, 2 works. Ooh. Let's see, 9 minus 15, 6, -6, 6. Yep, those work. And then had you graphed it and you thought about, it factored down to this, it's a parabola, it would have crossed the x-axis at 2 and 3. Then the x-intercepts would be at 2, 0, and 3, 0. It's all the same work. It just all depends on how the question's asked, is what they're getting at. Okay. All right. That's section 3.1. That's the part that's really on you. We've done everything we needed to do already this year to answer all those questions. All right. Now, the next part, though, is new. You've probably never heard this, but we're going to make a chart of all the types of numbers that you're supposed to have learned so far. So up until today, every single type of number that you've ever learned about is a real number. And there's a symbol for it. It's that weird looking R. Okay. So every single time a number you've ever learned about, real numbers. Now, real numbers are divided into one of two types of numbers. You have the rational numbers and the irrationals. Okay, rationals has a little shortcut way of saying it. It's a Q that's written kind of goofy looking, where they double up the sides. Irrationals, there's not an abbreviation for it. If people use one, it's because they're making up their own, but there's not a commonly accepted one. It's pretty easy. And here's the thing, if a number is a real number, it is one of these two things. Period. Okay. But what rational numbers are, it's any number that can be written as a fraction of two integers, where a and b are both elements of the integers. Now we're going to get to, I guess I shouldn't put the symbol. So if you could write a number as a fraction, where the numerator and the denominator are both integers, and integers, there's no decimals, no fractions. They're rational numbers, which it's kind of weird to, maybe I shouldn't give the definition as something I haven't written down yet, because y'all may not remember what an integer is. Okay, let me do it another way. Rational numbers, if you think of them as decimals, they're either repeating decimals or terminating decimals. So like if you had 0.3, repeating, that's the same thing as a third. That's a rational number. If you just had 0.3, because that's 3/10. If you just had 3, because that's 3 over 1. Those are all rational numbers. Okay, irrational numbers are numbers that aren't rational. So if you think of them as a decimal, they're non-terminating and non-repeating decimals. So the biggies are stuff like square root of 2, because If you turn that into a decimal, it would go on forever and it would never repeat a pattern. Anything with pi's in it, I should just say pi, or 4 minus 5 pi, or 3 minus 2 on the square root of 7. These are all irrational numbers. Now, if it's an irrational number, that's it. We stop categorizing. If it's a rational number, though, we keep going. So the next subgroup are the integers. And there's an abbreviation for it. It's Z. Oh, I kind of forgot to tell you what the Q was because I'm coming here now. So the integers are these numbers right here. We can list those. Okay. So it's just the rational numbers that don't have any decimals on them. Okay. So if I come back up here, now I can give the definition of rational numbers in terms of integers. It's any real number that can be written as a fraction of two integers. So like -7/5. That's a rational number. The reason why they picked a Q, or I'm pretty sure this is the reason. This is what I've always been told, but I never have confirmed it. That's horrible. I should have confirmed this. As if you can write something as a fraction, that's a quotient. Q for quotient. Okay, Z, they picked Z for integers because the German word for integers, I believe. Oh gosh, I should actually look this up before we talk about it in class today because I should probably confirm. But anyway, the German word for integers starts with a Z. So that's where that one came from. Now, if you knock the negatives off, then we're left with the whole numbers. So that would be just 0, 1, 2, 3, etc. And there's no abbreviation for it. And then if you get down to the natural numbers, there's an abbreviation for it. So weird looking N. Some people call these the counting numbers. So it's the same as the whole numbers. It's just you lose the 0. Because it's how many, like if you're counting things in nature, there could be a cow out in a pasture and it's missing a leg, but it's still a whole cow. So you say it's one cow. You don't say it's 0.9 of a cow. So how many can you count or something? So that'd be one of those. Okay. Now, the reason I'm bringing all this up, because now we're going to add a type of number. Now we're going to start having complex numbers, which the abbreviation for is the C. And it's any number that can be written in this form, A plus BI. Real numbers don't have the I's. Okay, and the I's we call imaginary numbers. I wish they had decided to call it something different because people think that means it's made up. That's not what it means. It's just what they decided to call it. Here's, and I guess we should probably talk about this. Like you came up with the types of numbers based on what you needed. Like the first types of numbers people use were the natural numbers. They counted things in nature. And then they decided, well, it might be nice to talk about the absence of value. Like, what if we had 0 of something? So then we have whole numbers. And then it's like, then they discovered, well, negatives could come in handy. What if I owed money? Or, I decided to go to the left of 0 on the number line. What's over there? And then we had negative numbers. And then, you had, well, what if we have a part of a whole? We have the rational numbers. And then the Pythagoreans were like, oh, well, how long is that side? Well, it's square root of 5, which is not a rational number. And then we have a use for these things called complex numbers, where here's by definition, here's what an imaginary number is. It is the square root of -1. Okay. Now, up until this point, you've always said that that's not a number. It's just it was not a real number. It's an imaginary number. And, oh, what just happened to the screen? It gives us an answer to this problem where, if it was x squared equals 3, we would have said, well, that's two things, either positive square root of 3 or negative square root of 3, that give us an answer. Now, we can, well, I guess I should get this. I'm not making much sense. I need to quit doing these at 4 o'clock in the morning because before my coffee kicks in, my brain doesn't work real well. There's actually just a sweet spot in the day that my brain does work real well. So, anyhow, it allows us to solve this problem and actually have an answer to it. We'll probably end up talking more about it. There's lots of, I don't know if lots is the right word, but there are uses for imaginary numbers. Like if you decide to become an electrical engineer, an electrician, impedance works just like imaginary numbers works. I don't want to get too deep in this today about what an imaginary number is, because if we go deep into it today, you'll be like, oh my gosh, there's so much going on, when it's really, really simple algebraically. So we're just going to look at it right this second as just, hey, this if I create this new set of numbers, then I'll actually have a solution to this. Okay. So if you've got I squared, that would be that squared negative 1, which is what I is, squared. Now think of this. What's the square root of 9 when you square it? Well, that's 3 when you square it. That's 9. You square square root, just drop square root off. So I squared is going to equal negative 1. And I'm hoping, this is really bad that I haven't gone to look and see, but I'm really hoping that this is not the only time in this book we talk about imaginary numbers. If it is, then I'm going to have to come back later and just give you some more information on it, because it's not okay that we hit this one day and we never talk about it again. But so you could do like, okay, I is an I, and I squared is a negative 1. Like somebody say, well, what's I cubed? Well, that's an I squared times an extra I. So it's a negative 1 times an I, so that's negative I. And I to the 4th would be an I squared that gets squared. So there's a negative 1 that gets squared. That's just a 1. And then if you just kept on, like I to the 5th, well, that's an I to the 4th times an extra I. That's a 1 times an I. That's just an I. Like it just starts repeating that pattern. I to the 6th is an I to the 4th times an I squared. So it's a 1 times a negative 1. It's a negative 1. Like we can just keep on going forever. Really, the only things you need for this section is that I comes about when you take the square of a negative 1, and that I squared is negative 1. Okay, you get that down, we are set. Because here's what's going on. Find the square root of each number. And up until today, you couldn't do this. You just said that is not a real number, and we wouldn't have done anything with it. But now we've introduced a new set of numbers, the complex numbers. And what the square root of 25, remember, if you have the square root of 6, you can break it down to square root of 2 times square root of 3. Okay, well, you can do the same thing here. This is a square root of negative 1 times the square root of 25. Well, the square root of 25 is 5. The square root of negative 1, we call the number I. And people like to put the i's at the end. Okay, so you just say it's 5i. You don't have to go through this step right here. If you see a negative under a square root, you just go, oh, that one's going to have an I on it. We're good. So same here. This is going to be the square root of 72, I. And 72 is 36 times 2. So there's 6 on the square root of 2, I. And that way right there to write it is fine. You'll see it written this way a lot, just because people don't want the I to get up under the radical. And when they put the I in front of the radical, that makes sure that didn't happen. This one, you got this negative 5 is getting multiplied by the square root of negative 9. Well, the square root of 9 is 3. It had a negative under it. That's an I. So you get negative 15i. Okay? And when we write complex numbers, you put them in this form, a plus bi. the a part's the real part. This is the imaginary part. And so imaginary numbers, these are both imaginary numbers, 2 plus 3i, 9 minus 5i. When the a part is 0 and there's just imaginary, people call those pure imaginaries, like negative 4i, 6i. And then real numbers don't have i's. Okay? Here's something that's kind of obvious, but people mess it up all the time. The only way two complex numbers equal each other is if the real parts are the same and the imaginary parts are the same. Oh, I didn't mean to put both of those. I guess I should put a set of parentheses around this. If you ever see me put IFF, that means if and only if. And if I do what I'm supposed to do, you won't see this because I'm going to go back and change the notes to being the right thing. So find the value of x and y so that this equation is true. Well, this complex number equaling this complex number, here's the real part because there's no I on it. So I know that the 2x has to be 10. I mean, x has to be 5. And the imaginary part would have to equal the imaginary part. So if negative 7i is what yi is, then y has got to be negative 7. And I've actually seen stuff like that on the ACT. It's just obvious, but people mess it up all the time. They seem to think it's hard for some reason, and it's not. And probably if you just had to guess, you would not mess up doing, especially when you're adding and subtracting. Like if you were treating I like a variable and didn't even know that it was a number, you would get the right answer right here. Like there's 13 plus 5 i's, and that's standard form. You get the real part first, imaginary part second. Like I said, it's just like it is a variable. It's not. It's a number. But like people don't mess this up. This is 7 minus 6i minus 3 plus 6i. So 7 minus 3 is 4. Oh, the i's disappeared. That's just 4. This one, we got 13 minus 2 minus 7i plus 5i. 13 minus 2 is 11. Negative 7 plus 5 is negative 2. So there's negative 2i. Yeah, that's no biggie. So those are going to go super fast. When you multiply, it's still pretty easy. This is a negative 24i plus a 4i squared. But remember, I squared is a negative 1. So this is really negative 24i plus 4 times negative 1. But write it in standard form. Put the real part first, imaginary part second. This one, we got to multiply it out. So there's negative 36 plus 63i's plus 8i minus 14i squared. Okay. So 63 and 8, so was that 71i? Remember, I squared is a negative 1. That's going to be negative what? 22 plus 71i. And we're good. Okay. And then we're going to use these when we solve quadratic equations as well. So like if you've got x squared equals negative 4, then x is plus or minus. Square root of 4 is 2. It has a negative under square root, plus or minus 2i. So remember, that gives you two different roots, 2i and negative 2i. This one, let's add 11. That's going to be what? Negative 36. Sure. Yeah. Divide both sides by 2. X will be plus or minus the square root of negative 18. Okay, I know it's I. 18 is 9 times 2. So that answer right there would be just fine. I'm just telling you, most of the time you're going to see it this way. So that people don't get the I up under the radical. If I want the zeros of this, then I'm trying to figure out what makes it 0. Plus or minus the square root of negative 5. But again, most of the time you'll see that I out front so that people don't lose the radical. Okay. I mean, lose the I up under the radical. And that's it.